All right, good morning, everyone. So it's 11:30, so why don't we get started? Uh, it's getting colder, so thank you for being here in spite of getting busier and colder. Now, before we get started for today, um, a few quick reminders and announcements. First of all, assignment 2 is already graded. So you can log into your Learn to take a look at your mark. And you can also view where you may have lost it at some points. In case of any, disagreement with the TA's grading, feel free to reach out to me. We can review your work together. Okay. And there's the final exam. One thing I didn't put here, but it's also important. Maybe let me add it quickly, which is the, the final project. Okay, the group project. And that's going to be due on December 5th, right? Finally, it's pretty close to the end of the term. Yes, please.
It's just that in like grades, it says group assignment and group project. So it's like there are 2 group assignments.
Oh, really? Oh, yeah. So let me take a quick look. So I guess... yeah, let me take a quick look at it to find out. Right. So actually, they look identical. So I don't know. Maybe I just hide one of them. So on your end, you will only have one. All right. So yeah, thank you for spotting this. I didn't even notice. Sometimes when I create the entry on Omni to Learn, sometimes it does some automatic stuff. Maybe I didn't notice something going on by Omni to Learn automatically, and then created a duplicated record. Yeah, thank you for that. Finally, the course evaluation is now open because it's pretty close to the end of the term, right? So the school requires every instructor to reserve like 10-15 minutes in class so that we can have a higher rate of participation. So the plan is that for next week, probably around the first break, we'll have about 15 minutes to do the course evaluation, of course on a voluntary basis, right? So it's much appreciated if you can provide some feedback and fair evaluations through this form we're going to reserve time for next week. Okay, so that's about some reminders and some information. Okay, so do we have any questions, any comments? All right, so let's then dive into today's content. So today we're going to continue with our discussion the k-nearest neighbor classification method. Well, actually, it's also can be used for regression, but for now, we are focusing more on classification, right? So last time we started to work on a Jupyter Notebook. This time, actually, I think it's better not to continue with that Jupyter Notebook. Instead, if you go to Module 9, Omni to Learn, under table of contents, I created a new Jupyter Notebook, which is called Product Returns and Cross-Validation. So in this way, you can download this notebook if you want to work together as we progress along in today's class. So by doing so, actually, we were able to redo some of the work we have done last time, right? And just to have a quick review of what's going on and what's the problem and what we did. All right. So the first thing we're going to do is to load the data set again into Jupyter Notebook. And remember, we were working on the product return problem. If you go to Omni to Learn, again, the data sets for in-class examples, the data set we were using is actually product returns. Right, let's copy the GitHub link and then let's try to import this data set again. So let's import pandas as PD. Right? And then let's do returns. I think last time we called it df returns, just to make it a bit more concise. Let's just call it return this time. Of course, you can choose whatever you prefer. Okay, and read CSV, and then copy this, paste this link to the data set. And then let's look at the first few lines as usual. Returns. So this is actually what's going on, right? So we have a data set. Each row in this data set is basically a purchase record. We have a number of features about this purchase record, including the category of the product that was purchased, right? And location of the customer, how many units were included in that order, and price of the product, right? Did the customer use a coupon for this purchase? How many returns were requested by the same customer last year? And then the total amount spent by the same customer last year. And then finally, our target column was the last column of this data frame, which is a binary variable indicating whether or not the product was eventually returned after the customer made the purchase. Right? We see 5 zeros for the return variable for this data frame for the first 5 records. I mean that for those 5 purchases, the product was not returned. If you see a 1 for a certain purchase record, it means that eventually the product was returned. So the retailer actually didn't make any money. All right, so that's our data set. And then we did a bunch of pre-processing steps. First of all, we performed one-hot encoding, right? So recall that the reason we want to do one-hot encoding is that we want to convert categorical variables into a numerical variable, typically in the form of 0-1 entries, right? So here we have product category and location and use of coupon. Those 3 categorical variables. So let's try to identify those categorical variables, or maybe we can call them features. Right? Features to encode equal to a list of variable names. First of all, we have product category with an underscore between the 2 words, and that's how it looks like in the data set, right? And then we have location. This is the location of the customer. And then we have use of coupon, but that variable is simply named the coupon. Okay, so I mean we don't have to give a name to this list of categorical variables, but sometimes it helps with the readability, right? Now we can do returns underscore encoded. That's going to be the new data frame we're going to create after performing one-hot encoding, right? So we can use PD pandas dot get dummies as usual, and then the first argument, remember the first argument is always the data frame you want to encode, right? So returns, that's the one we just loaded. And then when you want to specify the columns we want to encode, now this time it's already defined as a list of variable names, right? It's going to be features to encode, right? And then we can do drop first equal to true, right? Because if there are, let's say, 5 categories for a variable, we only need 4 columns, right? So that's something we have done before. And data type, d type equal to int, right? So integer value 0 or 1 instead of true and false. Now, this should be able to encode our data set and give it the name called returns encoded. We just want to quickly view the first few lines again to make sure that we have the right thing performed for us. Okay, looks okay, right? So, for example, for product category, we have 1, 2, 3, 4 columns, right? We have 5 different categories in the data set. Actually, maybe not just 4. 1, 2, 3, 4, 5, right? We have actually 6 categories for the different products in the data set, but we only need 5 columns to indicate whether or not each record belongs to one of those categories. And same thing for coupon and location, including city or rural. Anyways, that's the first thing we did for pre-processing, right? And then interrupt me anytime if you wish me to provide some more detailed explanations for those work we have done last time, right? And then we want to separate the features from the target. A fairly simple step, right? So let's define y equal to returns underscore encoded, and then we want to take only the returned column, right? And then for x, we're going to do returns underscore encoded dot drop. I want to drop the target variable. First of all, we want to drop, returned, right? But we need to drop more. That's why we'll drop a list of columns, right? So other than returned, we want to drop transaction ID, right? And we also want to drop customer ID, right? Because they don't include any information. They should not be included as part of the feature set, right? So after defining x and y, we want to perform feature scaling. Right? Remember, feature scaling is a must for k nearest neighbor because it's a distance-based method, right? So when we're doing k nearest neighbors for any given feature for which we want to make a prediction, right? We want to look for the k nearest neighbors, the data points in the data set that has similar features to the new record you want to make a prediction for, right? And then we don't want to have some features on a larger scale, taking on larger values or being more variable to be more important than other features, right? So we have to scale them, and this is a must for KNN, and not necessarily for logistic regression and other methods, even though they may impact on the training performance, convergence speed of the algorithm, etc. Right? Anyways, for now, the important thing is that we do need to do scaling because we're applying KNN. So in order to import the method for doing scaling, we have to import the submodule pre-processing, and from that submodule, we want to import the scalar we want to use, right? We have standard scalar, and another one we used last time was actually robust scalar, which is fairly similar, right? But then we are focusing on scaling the features based on the IQR and the median. But the idea is essentially the same, okay? So we can then define a scalar equal to robust scalar, right? And then we have to use that scalar we created from the robust scalar function, use it to fit and then transform our feature set, right? So we can do fit first and then do transform as two separate functions, but more conveniently, you can do fit underscore transform, right? That does the two tasks in one shot, right? Which is more efficient. All right, so after scaling the features, we're going to call it x scaled. Okay? And then that should be completing the scaling step, right? And finally, one thing we did last time is the train test split, which is essentially required for most of the learning algorithms, right? So we're going to import sklearn dot, this time it's model selection from there, we want to import train test split. Okay, and then we can do xtrain, xtest, just the part of the feature set after we do this splitting, right? So we want to extract the training set and also the testing set for the features, also for the Y part, the target part, right? And equal to the result returned by train test split, right? And then we want to split x scale, right? So if we don't scale it, we just simply scale the whole feature set. But then if scaling is desired or required, we have to scale the scaled data set. And then y, we don't scale y, right? That's the target variable. So just directly y. And test size is equal to any fraction you want to specify. And here, let's do, as usual, a 80-20 split, right? 20% of the data points will be reserved as test data set. And then random state for reproducibility, any integer number, we can assign it to the value 18 or any other value, right? Let's do stratify equal to y. Remember that the stratify argument basically guarantees that the ratio between positive and negative labels in the target column will be the same after the train test split. Right? In other words, if there's let's say 60% of the records are returned in the original data set, then after the split, I want to have the same ratio in the test data set and also the training data set, right? So we have done a lot of different things here. Let's run it. Hopefully it will not, but actually there's some error, so which is quite common. So yes, I forgot one thing, which is that when I try to drop those 3 columns from the whole original data set, right? We're dropping columns, so we have to do access equal to 1. And then that should be fixing this part of the error. And let's see if there's any remaining error. So now this time it went through nicely, so without throwing any error. So this part is done, okay? So this part basically does multiple steps. We went through that part relatively quickly today because we have done the detailed work last time. So again, we first separated the features from the target, and then we scaled the C feature set. We didn't do anything for Y. That's typically not required or not desired. And finally, we did the train test split, right? So do we have any questions? Yes, please.
So it's just an example that I was kind of working on with something like sort of a similar approach as to what you're doing right now.
Mm-hmm.
So it's like one hot encoding, right?
Mm-hmm.
Let's just say for turn column had 3 different variables, yes, no, maybe, or whatever, right?
Mm-hmm.
And then so what it was doing is like it was dropping like one of those 3 variables, like yes, for example,
Yeah.
and then it was creating 2 separate columns with like no or maybe. So so you put access equals to 1. Like is that what you do to fix it, or?
Oh yeah. So basically, one hot encoding was performed on the previous screen, right? So here, after I imported the data set, and then I specified the 3 columns where we have categorical values, right? And then I just use the pd.getDummies to perform the one hot encoding, and there's no access argument required here because by default you are encoding the columns. Right? However, here we actually were doing, using the drop function. Basically, in the original data set returns, even after encoding, we still included the customer ID and transaction ID, right? But I want to remove them. So basically, I'm dropping the transaction ID and customer ID columns. If I'm dropping columns, access equal to 1
Yeah.
is required. That's it. Okay. Make sense?
Yeah.
Okay, thank you very much. And then if we don't have any questions, let's move on to the next step. And this is also something we have done last time, right? So this is creating the k-nearest models for performing classification. So somehow, so let's sorry, I just accidentally changed the code cell to a markdown cell. So we need to create the k-nearest neighbor model, right? So we want to import another function. So this time it's again from sklearn.neighbors, and that's the library, a submodule of the sklearn library that includes many useful functions for k-nearest neighbors. So we're going to import k-neighbors classifier. Okay. Well, there's also a k-neighbors regressor, which is for regression, but right now we are focusing on classifier. So then after we import this function, we can use it to create a KNN model. Just to call it a KNN, but you can call it model or whatever name you feel comfortable with. Right? So then what we are going to do is that use this function to create a model. But when creating the model, right, so we need to specify how many neighbors you want to use. Well, actually, if you omit this argument, number of neighbors, I think it provides a default value, but it is more clear if you do it every time to specify the number of neighbors to use, right? Again, if I specify the number of neighbors to be 5, it means that for every let's say data point, a new data point outside my data set, I want to make prediction for that data point, and then simply I look at all those points in the original data set that has similar features. I'm going to pick 5 nearest neighbors that has similar features to the new data point, and then to do a majority of vote. Right? If the majority of those 5 neighbors predicts the product will be returned, and so will be my prediction for the new data point. Okay, so then the KN, after I define it and create the model, the next step is to do the fitting, right? So the fitting is usually ask the model to identify the relationship between X and Y, and we're focusing on a training set most of the time. And then let's run it. So this shows that the fitting was successfully completed. Okay, so that's create the model and fit the model. And then finally, that's basically what we did. Of course, we also showed the classification report to have a sense of the performance in terms of things like accuracy, precision, recall, right? Now this time, let's not repeat the classification report or the confusion matrix. Now this time, let's do something that is, I guess, straightforward somehow, but it may be somehow tricky when you're working on your own problem. It's a simple step, but people tend to forget about it. Right? So let me explain. So let's say we have 2 new purchases, not belonging to the original data set. Right? So let's say the first record is shown here. It's a product of the home category, and the customer is living in the city area, order size, price, and all those features. Right? So those are the features of the new purchases. We don't know the outcome yet. We want to predict for the outcome. And same thing for the second row. That's just another record of new purchases. And then we want to make a prediction. Right? So one thing we have to do first is that we have to convert those 2 data points according to the 1-hot encoded format. Right? Because when we did the training, we actually converted the category variables into the binary columns, right? And then we have to do the same thing here. So here, let's actually do things somehow manually. You can do it automatically. I think in the handout, I try to use a automatic procedure to make this work. But then I feel that it's a little bit too much petty details regarding how to implement some small tricks. Right? Here, let's just try to recall x dot for columns. That should be including, all the feature variables after we performed one-hot encoding. Right? So remember, we first did one-hot encoding, and then we separated the features with the target. So x should be including all those one-hot encoded columns. Right? So all those are just the feature names we used for prediction. Right? So let me just, from this output, I will just copy all of them. Okay, just copy all of them, and then I will construct a dictionary in order to, define the two new data rows we want to make prediction for. Right? So remember, dictionaries are, characterized by a pair of curly brackets. Right? So let me just paste all those variables, and then those will be treated as the indexes of the dictionary. And later on, we're going to create a data frame based on all those features. Right? So a little bit of moving things around to make the format somehow nicer. Okay, and those are the indexes of the dictionary. For each index, we need to provide a value, right? So later on, when we convert this dictionary to a data frame, if you still remember, those will be converted into column names, right? And the values corresponding to each feature will be a list of numbers to show the values of the different features for each of the variables, right? So I have actually, the data frame shown as a screenshot here. The new data points, right? So product category and will be home and sports, right? So let's see how we can encode that. Actually, the first thing here is order size, right? So let's look at it again. Order size will be 3 and 2, okay? So that's why I'm going to do a list of numbers, actually only two numbers. It's going to be 3 and 2, right? The indexes and values are separated by columns, okay? And price, well, let's check the first few, variables. All right. So later on, we're going to do things more quickly. So the price is going to be 99.99 and 12, and those are the price of those two products, 99.99 and 12. Okay. And return last year, you can go back to the original. Not the original, but the screenshot or the data, the new data points. Right. So here, let me just look at my record. Return last year. The first customer had 5 returns last year. The second customer didn't return anything, right? And total purchase last year, one is 300.45 cents, and the second one is $500.99. And then the product categories. So the first product is a home product, right? And the second is a sports product. So it means that for the category column of books, right? So neither of those two data sets actually are corresponding to purchases of books. So I will put 0 and 0, right? And then category, is it electronics, right? Again, home and sports, so 0 and 0, not electronics. Fashion, again, 2 zeros, indicating that for each of those two records, none of them is actually a fashion category product, right? Now home, the first product is home, so it's 1. The second product is sports, so it's 0, it's not home, right? So finally, for category sports, the first product is home, so it's 0 for sports. The second one is indeed a sports category product. And then there's also location. Location is going to be, the first one is in the city. The second one is in the rural area, right? So is it rural? The first one is no, so 0. The second one is actually indeed the rural area. And use of coupon, we have the first customer didn't not using the coupon, so it's 0. The second one, it's going to be use of coupon. So is the use of coupon be yes? Well, it's indeed a yes for the second customer, right? So anyways, that's a dictionary. So let's construct this dictionary. And then, so no error, great. So then we're going to define a new data frame. X new, let's call it X new, the features of the new purchase records, right? pd.dataframe is the method for creating the data frame. So it's just providing, the dictionary we just created as the argument, right? Now we can display X new. So at least in terms of formatting, look nice, right? So 2 rows corresponding to the 2 new data points we want to make prediction for, right? So that's the two new data points, right? So then let's do prediction. How do we do prediction? We know that with the model name is kan.predict, right? And then we can do X new. That's how we use the predict function, right? So we provide the features of the new data points, and then we call this prediction. But actually, something is still missing. I was wondering if anybody actually can spot what is maybe slightly off here. Right, so this is how exactly the 2 new rows for prediction look like, right? So, but then, in terms of syntax, and there's nothing wrong here, but there's still one step being missed here. What is that? Well, the hint is that we're usually actually using a KNN model, right? Any idea? Yes, please.
Is that the scaled version?
Exactly, right? We have to do feature scaling because the way we train the KN model is that we first scale the feature, right? And then we we actually train the model based on the scale features, right? As a result, when we are doing prediction, it's a must for us to scale the data first. And not just repeating the same scaling process, but we have to apply exactly the same scalar to the new data points, right? In other words, what we are going to do is that let's do X new. This time, let's also call it X new scaled, right? Equal to scalar. So what is scalar? Remember, we actually used the robust scalar function to define the scalar. And we fitted the scalar based on the original feature set, right? This time, one thing to keep in mind is that do not fit it again, right? So because for robust scalar, basically I'm subtracting the median of that particular column of the data set and then divide by IQR of the same column, right? Now I'm processing the new data points. I want to subtract the same median as the original data set, and then I want to divide by the same IQR of the columns in the original data set, right? So if you use fit transform or simply fit here again on the new data points, things will go wrong, right? Because in that case, we will be subtracting median and dividing by the IQR of the new data frame, which has only 2 rows, and that's not the right way to scale the new data points. We have to subject those new data points to the same scaling procedure as we did for the original feature data set. Okay, so this time only transform, no fit. That's the key thing to keep in mind, right? So now, after I have scaled the new data points, I will use the scaled new data points, right? And then this time we can finally predict based on the scale new data points. And the result, we can call it Y new, maybe prediction, right? Now, finally, to view the results, we just include the name of the variable that includes the prediction outcome in the last line of the code cell. And then we can, we can see the result, right? So basically, what we did is that we use the same scalar to scale the features in the new data point, right? And then we provided a prediction based on the scaled points, and then we made prediction. And remember, there are two new rows in the new data frame. Then, of course, for each row we make a prediction, we will have a total of 2 predictions, right? For those 2 new data points. Right? So we see 2 zeros, I mean that my prediction is going to be no returning. So for the 2 new data points, our prediction is that they are not going to be returned, right? So that's basically how we complete this procedure of applying KNN, right, to train the model and make predictions on new data. Do we have any questions? All right, so so basically there's some discrepancy with what I did before coming to this class, and I think that's because I used a different number of neighbors from what we did before coming to today's class. Okay, so again, important thing is that whenever you are trying to make prediction, try to recall if you perform scaling when you train the model. If yes, you have also need to scale the feature data from the new data points. Okay, so we're going to continue with this example, but our focus for I guess the remaining of the first session will be doing something we call cross-validation. Right? And cross-validation is very similar to somehow the train-test split. Right? Remember, the reason we did train-test split is that we want to train the model on the training data and then reserve the testing data for evaluation of the performance of the model. Right? We want to fit the model first on training data set, and then after fitting the model, we want to use the model to make prediction for the features in the testing set. Then we want to compare the prediction I get from the model for the testing data set with the actual observation in the testing data set. Right? And cross-validation is essentially the same idea, but we're going to do it in several iterations. So essentially it's an iterative procedure. The steps are outlined here, but let's just go to a particular example in order to understand this procedure called cross-validation. Okay? So whenever we say cross-validation, we need to specify how many folds we have in the cross-validation. So, for example, if we have 5-fold cross-validation, it means that the very first thing we do for performing the 5-fold cross-validation is that we take the original data set and then we cut the data set into 5 folds. Right? In other words, we simply divide them into 5 equal portions. Right? So this is the first step. And then we're going to perform 5 iterations if we are doing a 5-fold cross-validation. And let's see how we can do that. Okay. So in the first iteration, what we did is simply to label the first fold. We have 5 folds, which is 5 equal portions of the original data set. Right? We will label the first fold as the testing data set. And then the remaining folds will be the training data set. Right? So effectively, we are actually running a train test split, right? Then the yellow color, the fold with yellow color is the testing data set. And then the remaining 4 folds, I will just simply combine them together to form the training data set, right? So it's the same as train test split, right? It's a for 5-fold cross validation in the first iteration, it's simply a 80-20 split, right? So nothing is new during this iteration. We can train the model based on the green folds, and then we evaluate the model based on the test fold. Same thing as before, right? But we don't just stop with the first iteration. The key idea is that each of those 5 folds will serve as the testing data set for once. Okay? So in the second iteration, I will take the second fold as the testing part of the data set. And then I will combine the 4 green folds into the training data set. So this time, we're going to train based on the first, third, fourth, and fifth folds combined together and test on the second fold. Right? Again, the training testing is exactly the same in this iteration. The difference is that now we are letting the second fold also serving as a testing data set, right? And then we will have the third iteration where the third fold serves as the testing data set. And then we will have the fourth iteration and fifth iteration. So after we complete all those iterations, what happened was that every fold got a chance to serve as a test data set, right? So what is the purpose, or what is the benefit, do you think, is this procedure instead of doing just one train test split? It's essentially the same, right? But what is the purpose of doing this? So remember, when we are trying to do the train test split, and the testing data is some part of the data not seen by the training, by the learning model, right? So it's useful as something similar to the future. Basically, we're simulating the future by reserving some data as the testing data set. But then, if we only do the train split once, the downside is that the future is always going to be, random or unforeseeable, right? So we can use testing data set to simulate the future, but it's not that reliable, right? So in statistics, we know that it is more reliable if we take more samples, right? So by using this cross-validation procedure, what happens is that even though we only have one data set, but we get to extract 5 different simulations of the future, right? In other words, we're taking 5 samples to simulate the future. Right? 5 samples of the future is better than only 1 sample of the future, right? So this will essentially, or in most cases, make your evaluation measures of your model being more reliable, because now what you can do is that for each iteration in the cross-validation procedure, I can train and test the model, right? And then I got one set of performance measures, such as recall, precision, accuracy, the AUC score. Now, if I do 5 iterations for the 5-fold cross-validation, I will get 5 sets of performance measures. So then eventually what we want to do is to average over all those 5 sets of performance measures to get the overall performance measure, which is supposed to be more reliable than simply doing one train test split. Okay, so that's the idea. Any questions? All right, so let's see how we can actually implement this cross-validation procedure. Right? Even though it sounds a bit tedious, because you have to repeat the same procedure 5 times. If you're doing 5-fold, 10-fold, you do it 10 times, right? But the code is actually somehow quite concise. There are 2 steps for implementing cross validation. The first one is to specify or define the strategy for doing cross validation, and this is achieved by one simple function called stratified k-fold. So let me try to provide an example, and then we can also try to understand the meaning of this function and how it can specify a cross-validation strategy. Okay, so again, we need to import some modules. So this time it's going to be again sklearn dot model selection, because cross-validation is as we will do later. It's actually a technique mostly used for us to tune hyperparameters and select the best model with different hyperparameters. So let's import stratified k-fold. All right, and then we can use it. We're going to define a stratified k-fold method by using this function, but we need to actually record the result returned by this method. So let's call it stratified k-fold, all in small letters, okay, just for readability. And then this is the outcome of the stratified k-fold function. We need to specify, I think, 3 arguments. Right? So first of all, we have the nSplit, nSplits actually, and splits equal to 5. Right? I mean, you can let it equal to 10 or any integer number, but if you set it to 5, it means that we're doing a 5-fold cross validation, right? We're cutting the whole data set into 5 equal portions. If you do 10 and you're cutting the data set into 10 portions, the idea is essentially the same. Right? It's just 5-fold or 10-fold. One of them is usually the commonly used cross validation strategy, right? And the second one is called shuffle, and here I'm doing shuffle equal to true. Right? So as we have seen in the previous illustration, right, if you say you don't specify shuffle equal to true, then what it does is that it simply cuts the original data set sequentially. Right? Let's say you have 50 rows and you do 5-fold cross validation. Then the method will simply, cut off the first 10 rows as the first fold, right? And then the second 10 rows as the second fold, so on and so forth, right? But sometimes we want to have some randomness, right? Because maybe it's not a good idea. Let's say all the data points are organized by time, right? So then I don't want each fold to only include data points that are corresponding to purchased during the same time period, right? We want to have some randomization in order to, for example, training the model, want to get a sample of the big picture from the whole data set instead of focus on a very particular part. Let's say purchases made from 3 months ago. That's the main reason, right? And then if you specify shuffle equal to true, you have to do random state because you have used the randomization, right? So providing a random state will allow for reproducibility. Then that's it for defining the strategy for performing cross-validation, right? And that's just an intermediate step. The second step is that we have a function to use, which is called cross-val score. So basically, this will perform the cross-validation procedure by using just one simple function, right? So again, we need to import the module from sklearn.model selection import cross-val score. Okay, I mean you can import it along with the stratified k-fold method, but here since we're using a new screen, let's do it again. Okay, so let's see what is returned by this function. So we're gonna call the return result as CV for cross validation, CV scores, right? And then let me copy and paste the name of this function. We will need to provide some, arguments, right? The first argument is the model, right? Because cross-validation is built on top of the learning model, right? So in each iteration, after I split the data into training and testing part, we still need to apply a learning model. So here it's KNN, right? I mean, you can use any other learning model, like logistic regression or anything else. Okay? And then we need to provide X and Y. Here it's X scaled. Right? Remember, X scale is the scaled feature for performing KNN. And then CV is the argument for cross-validation. It's a keyword argument, and it's going to be equal to stratified k-fold. This is exactly the strategy we have defined on the previous screen, right? And scoring, because every time I actually combine the 4 folds into the training set, and then I want to train and testing the performance on the testing fold, right? I have to calculate a score, but we have a number of available scores to investigate, right? So it can be accuracy, it can be precision or recall, right? So let's do maybe ROC AUC, the AUC score, okay? And then after performing this operation, let's look at what is actually returned by this function, simply by typing the name of the result in the last line of the code, right? Well, we can see that we have 5 numbers in the list. So what are the 5 numbers? Because I have specified score equal to ROC AUC, so those are AUC scores. Remember, we did 5 iterations for the cross-validation. So for each iteration, we have a train test split. We can get a performance score for each of the iteration, right? So those 5 scores are exactly the AUC scores you get from each of the 5 iterations within the cross-validation procedure. Okay, so that's basically how we can implement, cross-validation, right? So finally, before we have the first break, let's actually do one more thing. So CV scores, that's exactly the 5 numbers, right? So what I'm going to do is simply to calculate the mean value. So that's a NumPy array. It has a method called mean, which calculates the mean value, right? So basically, this mean score across the 5 performance scores is going to be the main performance measure useful for subsequent steps of model evaluation or model selection, right? So I have specified to use 5 neighbors for this example, for training this model, right? So what is the performance? Well, I mean, for 5 iterations, we get 5 different performance scores, but the overall performance with respect to the AUC score for doing KNN with 5 neighbors, now by doing the whole procedure, we can say that the overall performance in terms of AUC score is around 80.73%. Okay, so that's the main idea. So before the break, we went through the procedure of cross-validation. The key idea is again to divide the whole data set into folds. Let's say 5 folds cross-validation. Then we perform 5 iterations. It's important to remember that for each iteration, we actually have a training set and also a testing set. All right. So when we do the training and then testing, we still need to use a certain learning model. Like here, it's the classification method provided by k-nearest neighbors. Right? You can use an alternative neighbor model, right? So something important to keep in mind that cross-validation is a procedure built based on a certain learning model. Right? That's why in this function, cross-val scores, we always need to specify the model you created earlier for which you want to run cross-validation for. Okay, and before we move on, there's one thing I want to draw your attention to, right? So here, then we also need to provide the feature and the target, right? So pay attention, here it's S scaled and Y. Those are all the rows in the original data set, right? We didn't use only the training data set. That's because in this cross-validation procedure, for now, what we did is that we want to create training and testing data sets in different ways according to this method, right? So that's why inside cross-validation, we are actually doing training and testing split. And that's why we didn't particularly focus on the testing data set. Training data set, right? So that's one thing to keep in mind. But however, in the next example, we're going to focus on another aspect, which is hyperparameter tuning. In that part, things will become a little bit different. And when we get there, I will explain once again on how things are different in terms of, which part of the data you want to perform cross-validation on. Okay. All right. So then we have the next part, which is to do some hyperparameter tuning. Right? So here we have only one hyperparameter, which is the number of neighbors. Right? Remember, hyperparameter is something that is not chosen by the learning model. So remember, when we created the KNN model, we specified the number of neighbors to be a certain number. I just used 5. You can use any other different number of neighbors. Right? So the KNN model is not really doing anything about the number of neighbors. It's given to the model. Okay? But still, from the perspective of the person who is implementing this method, we will be interested in determining the right number of neighbors. Right? The idea is the same as before when we were dealing with things like selecting variables, selecting features. Right? So it's always the case that we want to choose the value of the hyperparameter, in this case, number of neighbors based on their performance. Right? So if, let's say, using 20 neighbors has better performance than using 10 neighbors, then it's logical to use 20 neighbors instead of 10 neighbors. Right? So that's the critical idea. The same idea has been already discussed when we are doing variable selection or feature selection, but here we actually have a new method which is called grid search CV for cross-validation, which make the coding very compact. Okay, so let's take a look at the whole procedure. Okay, so let me actually show you the whole high-level procedure using a couple of slides. Right. So this time we start with a full data set, which is the customer purchase return data set. Right. So this box to the left-hand side represents the entire original data set. So for the procedure we're going to run, which is called grid search cross-validation, for selecting the number of neighbors, the first step we do is to split the data set into train and test parts. We have 2 parts, train and test. Okay? And then for hyperparameter tuning, we're going to focus on training data set. Okay? We're going to apply this function, and the details is yet to come, but we're going to apply this function on the training set. The purpose of this function is nothing but to determine the best value of the hyperparameter. In this case, number of neighbors, right? So essentially, we're trying different number of neighbors. And what happens if we have 5 neighbors? What happens if we use 15 neighbors, 20 neighbors, 100 neighbors? We try a set of predefined values. Then we'll see which value will give me the best performance. Okay? So this procedure, implemented by grid search CV, give us the model with the best parameter. Right? Once we get the model with the best parameter, we will go back to the test data set, right? looking at this whole procedure, it hasn't seen the test data set yet. So this part, testing set, can still be utilized as some kind of simulation for the future, right? So then, eventually, for the model with the best parameter, we can apply that model to the test set to get some idea about the performance of the model after going through this hyperparameter tuning procedure based on cross-validation. Right? So inside cross-validation, same thing as we just did. If it's 5-fold cross-validation, we just let each fold to get a chance to serve as some testing portion of the data to provide some performance score, right? So then for 5-fold cross-validation, we'll have 5 scores. You need to specify which score, right? Accuracy or precision or whatever. Then we have 5 scores. Then we average over those 5 scores to provide an overall score from the cross-validation procedure. And then cross-validation procedure is part of this function, okay? So basically, I run cross-validation for each possible value of the hyperparameter and see the overall performance score based on cross-validation. Okay? Then after I have the score from based on cross-validation for each possible value of the hyperparameter, number of neighbors, then I can compare the models with different number of neighbors to pick the best one. Right? Once I get the best one, I can go back to the test part of the data set to simulate the future, to have some idea about the performance of the model on some data points you have not seen in your entire training process, including in the training inside this procedure by a particular KNN model, and also this procedure of tuning the hyperparameter using grid search CV, right? So the whole procedure is a little bit maybe complicated, but the main idea is that we are putting different elements together, right? We first of all have cross-validation as a method to provide an overall score based on several iterations. And then we also have the procedure of enumerating over some possible values of the hyperparameter to see which one is the best, okay? So we're gonna dive into the details, but before that, do we have any questions? All right, so we're gonna first import the required function, grid search CV. By the way, this is one of the few popular methods for doing hyperparameter tuning. Later on, if we have time, we are going to do randomized search CV, which is essentially the same. But then let's first do this one first, and then we'll explain the details when we are implementing the function. Okay. So again, it's part of model selection because we're tuning the hyperparameter. It's essentially selecting the best model within a given set of candidates, right? So we're going to import grid search CV. All right, so this is the first step to import the required module from the corresponding library. Then we're going to define the parameter grid. What is the parameter grid? Well, parameter grid is simply the set of hyperparameters, in this case, the number of neighbors I want to test out. Okay, so here let's do param grid as the name of this parameter grid in the form of a dictionary. Right. So we only have one parameter to tune, which is number of neighbors. So n neighbors. Well, pay attention here. The index of this dictionary must be exactly the same as the corresponding arguments for the learning model, right? Remember, when we create the KNN model, we have to specify n neighbors equal to 5, for example, right? So if the argument is called n neighbors for the KNN function, then we have to use exactly the same name, right? So n neighbors, then we can specify a list of numbers, right? For example, we can do, for example, 5, 15, and 20. So then it means that the whole grid search cross-validation procedure will try those 3 values. Okay, let's actually make it slightly more complicated here. So I'm going to define range from 1 to 102 with a step size of 4, right? I mean, this is something we encountered before, right? So for range, we need to specify the starting index, stopping index, and step size. So this range from 1 to 102, that's actually stopping before 102, right? Stopping at 101. So basically it's 1, and then with a step size of 4, the next number is 5, and then another step size of 4, next number is 9, and 13, 17, until 101. Okay, so this is essentially the same as providing a list, but I want the list to be a bit longer so we can try out as many values as possible for performing k-nearest neighbor classification. Okay, so this is the parameter grid, and we define it as a dictionary, and we'll use it shortly. Okay, now we're going to define the model. Actually, we already defined the model, but let's actually define it again. So k-neighbors classifier. Same as before, but this time I'm not providing the number of neighbors because that's something we're gonna try out, right? I mean, if you want, you can say n neighbors equal to 5, but it doesn't matter because later on we're gonna try other values in the parameter grid anyways. Okay. All right. So this is the step for defining the learning model. The next step is that we're gonna define the grid search. Okay, so then we can call it grid search. This is something like, again, like a model, but it's not just the learning model. It's more like the hyperparameter tuning model. And this is defined from grid search CV. And we need to provide a few parameters. The first one is going to be KN, the learning model, right? It doesn't have to be KN, and it's more like whatever learning model you are hoping to use. And then the second is the parameter grid, so param grid. All right? So this is defined just a few lines above, right? So it's just a range from 1 to 101 with a step size of 4. And then the third one is the CV equal to stratified k-fold. Well, because for each step of the hyperparameter turning procedure, we need to evaluate the performance corresponding to every value of the number of neighbors we specify in the param grid variable, right? But then for each step corresponding to a particular value of the hyperparameter, we need to use cross-validation. Whenever we use cross-validation, we have to specify, is it 5-fold, 10-fold, and do we do shuffle randomization? But here, this stratified k-fold is already defined when we are running the 5-fold cross-validation, right, before the break, so I can directly use it. If you want, well, if it's not defined, you can just define it again by using the stratified k-fold function, right? Finally, scoring. Scoring can be things like, again, IOC, AUC, or you can use accuracy, F1, and there are a number of options that we discussed earlier, right? Now, this step is similar to defining any other learning model, right? It defines the model, but we haven't used it to fit the data, right? Because in order to run the whole procedure, each step of the procedure actually requires the use of the data to fit the model, okay? So what we can do is to do grid search. That's something we define, but then we need to fit it to the data, right? So this time I'm going to do X train, Y train. And this is actually obtained in the beginning of today's class, right? So this time I want to focus on the train data set. I mean, if you really want, you can use X scaled Y to use the whole data set, right? But in that case, you will be using all the data to run this procedure. It means that after we have completed this procedure, all the data points in the data set has been used, so you don't have anything to simulate the future, right? So this time I want to only use the training part from the very first train test in today's class, and then there's still a small portion, 20% of the data points unseen by this whole procedure that can be used for simulating the future. Okay, so let's try to see if it can work out. I guess I have a typo here. K neighbors classifier. Capitalize the N. So, but then K. Oh, sorry. K neighbors. Okay. So it takes a while, right? Because here I'm trying a relatively large number of hyperparameters. But it's a finished, I guess, after like 10 seconds or so. Anyways, if you get this result, it means that things are already accomplished, right? Again, we only have a few lines of code, but there's actually a lot of things going on behind the scenes. But for our purposes, well, our priority is to being able to build a model, to apply them to, real-world problems, right? So for our focus, it should be this line. So we define the grid search, and the grid search is for us to testing out different values of hyperparameter, number of neighbors, right? For a given number of neighbors, we use cross-validation, so you have to specify cross-validation procedure strategy, right? And then for each iteration of cross-validation, you have to specify a particular model, right? So I think it's quite a few things going on, but if you try to, refer back to the notes in the handout and also in the slides, I think the picture will become more and more clear. Okay, so after this procedure, after fitting the grid search cross-validation procedure, behind the scenes, the model has already chosen the best number of neighbors for us, right? With respect to the given scoring, measure, which is AUC score for now, right? It is under any other performance scores. Now, after the model is trained, all the information is contained in the trained grid search model, right? Grid search procedure. So, for example, we can easily retrieve the best parameter and also the best score. Right? So every parameter is corresponding to a particular performance score based on cross-validation. Now, since the model is already trained, we can take a look. Okay, so remember the grid search is something we just fitted. Okay? And then grid search dot best params ending with an underscore. That attribute will be giving us the best number of neighbors. That's exactly the hyperparameter we're trying to tune, right? Let's take a look. So it says that n neighbors is equal to 13, right? So that's exactly the best number of neighbors found by this method. Right? So how many neighbors should we use? Initially, we didn't know, right? According to this procedure, it suggests to use 13 numbers for doing classification based on the KNN model. Okay, this is a dictionary, right? Because initially we provided the parameter grid in the format of a dictionary, and then if we want to extract this number, we should be using square brackets and call on the index in this dictionary, which is 13. Right? So this is the first parameter. First thing we're interested in. The second thing is that, again, from grid search, we can retrieve best score. All right? So it's 0.82. Remember, we're using the ROC AUC score, right? So out of all those different numbers of neighbors to use, using 13 neighbors is the best according to the AUC score. And the corresponding best AUC score is 0.82, right? So this is what's going on here. All right, so let's use print out the information, use a better format. So let's do an F string, right? Let's say best number of neighbors is equal to curly brackets which is 13, right? But this number 13 is returned by the best parameters. But it's a dictionary. We have to extract the numerical value by calling on the name of the index. So this is the first thing, and then we can say best AUC score equals the second thing, right? So grid search dot best score. That's actually 0.82. Okay. So anyways, you don't have to do this, but sometimes this actually makes the whole thing a bit more readable. Okay. All right. So do we have any questions for using this hyperparameter tuning procedure? Okay. So one more thing. Again, the grid search object after fitting based on this whole procedure, right? For this time, there's one more attribute, which is the dot best estimator. So let's retrieve that attribute and call it KNN best. Well, this time it does not return any particular value. Instead, it returns the best model. Right? So what I get from this command by assigning grid search dot best estimator, which actually should end with the underscore, assign it to a name called KN best. This is the KN model with 13 neighbors. This is the model. Okay. If it's a model, what we can do is that we can use the model to make predictions. Okay. So basically, what we can do is that we can make predictions based on the new data. Okay. Or maybe we can make predictions based on something like the test data, because we haven't used the test data yet, right? So let's try to go through this procedure. So now we have retrieved the best model. It's a model, right? It has all the trained trained procedure inside the KN model. So what's going on next is that we can use KN best dot predict, and we can predict based on X test, right? And then I can call it Y pred. Okay, so this will give us the prediction on the test data set by using the tuned model with 13 neighbors. Okay, now what I can do is that I can do the same thing as before, right? We can import sklearn dot metrics. It's actually from this module. Import. Let's do the classification report. Right now, I can do CR classification report equal to this function classification report, and we compare Y test with Y prediction. Okay, so then we can print the classification report. So this is the performance of the best model after this whole procedure of hyperparameter tuning, right? So the whole point is that I didn't know what is the right number of neighbors to use. So I went through this procedure. I find that it's best to use 13 neighbors. And then I retrieve the model with 13 neighbors. What is the performance? And with respect to precision, recall, F1 score, all those things we have discussed before, and this shows you the picture, right? We can also do let's say the ROC AUC score. Okay, and in order to do the ROC AUC score, because the reason I want to do this is because I want to see if there's indeed any. Well, actually, maybe we can skip this step, right? Because I just recall that we already get the best ROC AUC score being 0.82 something, right? So remember when we use 5 neighbors early on in this class, we get something like 0.880 something as the ROC AUC score, right? So it shows that actually after tuning, we did get a bit of a boost in terms of the performance we are focusing on for for the tuning procedure, right? Well, this is actually the whole procedure to make the model better by finding the best value of the hyperparameter number of neighbors. Okay? Okay, so there's also a line where you can also make prediction based on the new data set, right? So let's quickly finish that as well for completeness. So the best KN model, this time I'm going to predict on X new scaled. Now the result is different, right? So now I predict the first data point in the 2-row data frame we constructed earlier to be a return, right? So, and that's because now we have supposedly a better model after tuning, right? Initially, I said I use 5 neighbors, but that's really an arbitrary number. So in terms of reliability, I would say that it's more reliable for this new prediction outcome than the one I used before. Okay. And one final remark about this hyperparameter tuning procedure through grid search CD is that when we are using this function, we provided the training data set as the arguments for the data part, right? So that's because we still want to reserve the test data to simulate the future, right? So as long as we've complete the whole procedure of manipulating data, making predictions, and tuning the parameters, in the end, we always want to ask ourselves this question: do we have some data left to simulate what may happen in the future, right? So that's why we only use the training part, right? If you don't care about simulating the future, let's say we only want to focus on the performance in the within the data set, and then you can use the full data set. But it's usually a good idea to always set aside some rows as the testing data for simulating the future. Okay, so do we have any questions? All right, so we still have 10 minutes before we have the second break. So let's get started a little bit about the next part. So this time we're gonna move on to talk about the tree-based methods. Tree-based methods are really a class of very powerful methods that's known to have accurate performance in many real situations. You probably know that data computation website Kaggle. I would say the vast majority of the competition winners there, more or less that they are using things like XGBoost or some other methods that's actually based on tree methods or forest methods, right? So let's recall the main idea of supervised learning. Very simple: prediction based on feature, right? Predict Y based on the feature set, certain feature X, and then F, the function, is to help you map your feature into the outcome, right? And we have talked about KNN and logistic regression, which are performing the same task. How to map the feature into the outcome. And decision tree and random forest are nothing different. Okay, but let's mention maybe the most important concept in decision tree. The most important idea is to do some branching. Okay, so we're dividing the data set or the feature space into branches. So for features located in certain part of the feature space, we're making a particular prediction in terms of classification or regression. Here we're focusing more on classification, right? And let's look at one example, which we will also implement in our Jupyter notebooks. This time we're predicting sales levels of a particular product, and we'll be focusing on sales levels of car seats for children. Okay, in the data set we're going to load, maybe in the next session of today's class, we will see a number of features but for in the slides, in terms of demonstrating the method, right? Let's focus on only two features because we can plot two features in a two-dimensional figure, so it's more intuitive to understand. Let's focus on two things. In our data set, we will have different rows. Each row is corresponding to a retail location. At that retail locations, we're trying to sell, car seats. Okay. Now, the feature include the average age of that location and also the average income of that location. Okay. So basically, age and income, those are not, in this context, it's not age and income of an individual. Instead, it's looking at a certain retail location, maybe a neighborhood or a city or a region, and then what is the average age and average income in that region, right? And the target variable to predict is sales level, not particularly the sales number, but in the example we're going to look at, we first focus on sales level. High meaning that we have sold annually more than 7,000 car seats. Low means that it's below 7,000 car seats, right? I mean, because we are focusing on classification, and also because predicting levels is generally easier than predicting precise numbers, right? So, decision tree essentially provides a diagram like this one. But if you look at it, it's more like an upside down tree, right? At the top, we have the root node. In the bottom, we have those four rectangles representing the so-called leaf nodes, right? So it's an upside down tree. And the idea is branching. We use branching to define the criteria for making predictions, right? So in each node of this tree, we see a certain feature. And here, we only focus on two features, average age and average income of a certain region, right? We also see a number inside every node. That's actually a threshold for the corresponding feature, right? What does it mean? So, for example, let's say we're thinking about establishing a new retail store to sell car seats at a certain region, a certain neighborhood, right? And then I will ask myself questions based on this tree. Right? The first node is age. So the first question is that whether or not the average age of this new location is above 50. Okay? Let's say I have a location and then I did some consumer research. Right? I find that for this new location, the average age is 35 years old. Right? And then I will go to the left branch. Okay? So the right is greater and the left is smaller. So if I'm looking at a record or a location with an age 35 years old, it's below the threshold. So I go to the left branch. Okay? So the next thing I want to look at is the income. And the threshold is 100,000. Right? Let's say the income level of this new location on average is 200,000. Okay? And then it's greater than this threshold. So I will go to the sub-branch to the right. Right? And that's how I make a prediction. So at the leaf node, the prediction is high. Right? If I have a decision tree like this, and I look at a new data point, says average age 35, average income 200,000, and then I end up in this leaf node, my prediction is going to be high. Okay? That's exactly how we can make predictions based on a decision tree. Of course, this is something like a trained tree, right? So based on which we can already apply this tree to make predictions. Okay? So do we have any questions for that? Okay, so here are some explanations. But anyways, so a few minutes left. So let's get started with looking at a particular example. Okay, the same example. This whole two-dimensional plane that represents the feature space. A feature space is all the values, the set of all possible values of your features, right? And here we have points. Those are the points in the data set. Let's say we have this blue point here, right? It represents a location with an average age maybe 59 years old, and the income level is somehow low. It's maybe $10,000 annually, right? So Well, those points here are just simply what's already in the data set we will have, right? I mean, potentially for any new locations, you can be located anywhere in this feature space, right? Maybe somewhere here, then its average age is 15, and average income levels, 120,000, or any place. Now, red points corresponding to locations in a data set with a high sales level, above 7,000. Right? Blue points corresponding to low sales level, which is below 7,000. That's what's inside the data space. And then, in order to construct a decision tree for us to make predictions, we want to do branching. Right? How do we branch? It's already on the previous slide. We want to pick a feature and then define a threshold on the feature so that we can divide the whole feature space into two branches. Okay? Now, one example, let's say I pick the feature age and the threshold 49. So we're cutting the feature space into two parts, right? Below 49 years old and above 49 years old. I mean, you don't have to actually use age or the threshold 49, right? I mean, you can choose income, you can use a different threshold, but again, it's part of the training process for you to determine which feature to use to make the split, to do the branching, and what is the right threshold level to use for the branching, right? So let's say we have decided to use 49 on age, then we have two resulting regions. Right? It's actually a bit nicer than before the branching, right? Before the branching, we have blue and red points. Now we still have blue and red points in each of the two branches or each of the two regions. Right? But one thing being nice, what's one thing being nice? If you compare before and after doing the branching. Yes, two clusters, that's right, but what's something nice within each of the clusters? Well, if you look at the right branch, right, we have 3 red points and only 1 blue point. Right? So if I have to assign a label to this region, I will predict high sales because there are 70% of the data belong to the red class, which is high sales. And same thing, to the left, it looks like a blue region. It looks like a low sales region, right? In other words, what's happening here is that each of the resulting two regions are somehow more pure than the original entire feature space. Right? More pure means that there seems to be a more dominant class if you look at the data points here, right? So that's something we call some measure we're going to make use of, which is basically purity or impurity, right? So basically, we're going to need to use some concept called impurity measures, and generally there are two options. One is called Gini index. I think we more or less all know Gini index, right? So it's more like an inequality measure. So here we call it impurity measure. If you have more diverse data points in a certain region, it's less pure. But we want it to be more pure in this case, because if in a region we have a more pure data points, meaning that there's one predominant class, maybe high sales class, and then I can predict that within that region, I will classify all the new data points in that region to be high sales. Right? That's my prediction. Right? If the data points are more pure, it's easier for me to make the prediction for a particular region. Right? Entropy is another thing. So I have the formulas here, but let's not focus on the mathematical details. All we need to keep in mind is that we have those two impurity measures that measures how pure is a certain region. Right? If I have a low Gini index, or if I have a low entropy value, then it means that that region is more pure. Right? If it's pure enough, let's say the value is fairly close to 0, it means that most of the points in the region, let's say, is blue. And then I can say that maybe for any new data points in that region, I will predict that data point to be a blue class or low sales level, right? So that's how actually the main criteria useful for us to make the split, right? How do we make the split? Well, I can choose age and define threshold, or I can choose income or choose a different threshold, right? But what do we do exactly is that I want to pick the kind of feature and the kind of split that results in a higher degree of purity. Right? So that's the main idea for selecting the features and defining the thresholds. I mean, there's of course a lot of details, but all the details will be something like the behind the scenes parameters, right? So we don't have to worry about the details, but only focus on the main idea. Now this is what we get before the breaks, right? So we use a threshold of 49 years old to do the branching on the age feature. Now, if we want to really start to make predictions, that's already usable, right? So after dividing the region into two branches, I can just say that if your new data point is in this blue colored region, then I predict that the label is blue, or I predict that the sales level is going to be low. Right? If your new data point for a new retail location is to the right of this threshold, 49 years old, then I can predict that the sales is high. Right? But alternatively, we can continue with the branching process. Right? Should we continue or should we stop? Well, this is another thing that is determined by hyperparameters. But let's say for now, we want to continue. Right? And then by continuing, we mean that for each of the regions we see here, two regions, right, we can further split them. For example, in the red region to the right-hand side, if we want to do a further branching step, how do we do? Which feature should we use and where should be the threshold? So what do you think? Focusing on the region for ages above 49 years old, and then I want to split that region based on either income or age, and also by defining proper threshold. What should we do? Remember that we want to minimize impurity, right? We want the resulting region to be as pure as possible. So what do we do?
Around 48,000.
Exactly, right? Because you see, we have 3 red points above and a low blue point. If I use a threshold somewhere here, and then I will cut the region into 2 parts which are 100% pure, right? This is exactly what we can do. So for income level, here the exact level I'm using is 39,500, somewhere here. And you can use 40,000, which will give you roughly the same, not roughly, exactly the same result, right? So by doing another branching step based on income for the right-hand side region, income above 39,500 or below that level, we have 2 sub-regions. And one of the sub-regions, which is the one on the top, will be purely red, right? And the one in the bottom will be purely blue. So that's one more step we can do, right? We can also further split the region to the left of the age threshold, 49 years old. Now here what I'm doing is that maybe I can further split on age, because by doing a cut around 24 years old, what happens is that in the middle region it's predominantly blue, right? So it's kind of being a bit more pure than before the splitting, right? And then I can continue the process for the left-hand side region for age below 23.5 or around 24, this part, I can further do a split vertically, and then this time I can get 2 other pure regions, right? So look at the sub-region to the left. If I further split at the income threshold of 59,000, right, and then above that level I have 1 red point, below that level I have 1 blue point. So those 2 regions will be pure, right? And in the middle region, I can do similar things. I can try to separate out the red point. There's only 1 red point, right? So if I use the threshold of income level around, I think here I'm using 102,000, right? And then we will see that we get a pure region, which is below that threshold level. Every point is blue, right? So we get a blue region, and then we still have two different color points in the top region, so I need to do a further split, and then I can get the pure regions. In the middle, I add two threshold levels, divide the middle region into three parts, so we have two blue regions and one red region. Now, there's no point of doing further branching, right? Because after all those branching steps I have just performed, every region is pure. So based on the data, generally we will consider it the case that there's no further need of branching because now every region is pure, right? So this is something we call a full-grown tree. We keep branching until we have the subregions, each of them being a pure region. We don't have two different classes inside each region, right? Now the question, before asking the main question of whether or not we want to do a full-grown tree, let's actually represent the whole procedure based on this diagram, right? So it's the same thing as what we just done for splitting the feature space. So first of all, we use the feature age, and the threshold is 49. So above 49, we have two branches, right? And from the right-hand side region, we further use the income to split the region vertically. So below and above the threshold 39,500, we have two regions that are pure, so I can stop there for this branch, right? So below that income level for age greater than 49, sales is low. Above that level, it's high, right? And for the other branch, I further define an age threshold to split into two regions, right? And then for the leftmost region, I further look at the income levels to split into two subregions which are pure. For the middle branch, I need to introduce two more splits, right? And first of all, based on the income level of 102,000, and then a slightly higher income level, eventually we'll get all those leaf nodes which represent the pure regions. And this is what we call a full-grown tree. You split until there's no further room for increasing the purity level, right? So that's the full-grown tree. Now, the question is that, do we want to, yes, please.
So like one of the things I was kind of thinking is like, so a lot of that is basically, it could be like trial and error and also based on like how familiar you are with the data set already, right? Is there a way to validate that? Like, for example, like, you brought up the topic of entropy, right? Is there a way to calculate that to kind of validate if this is how I fragmented the tree and also this is like the entropy value as well, so it validates like the decomposition of data.
Oh, exactly. So this is the high-level idea, right? So later on in Python, we're gonna use a method to construct tree. After you construct tree, you want to actually train the construction of the tree in the sense that you want to make the split so that you can decrease the entropy or Gini index in the most efficient way, an effective way, according to what you have in the data, right? After the whole process is done, and then we can look back to retrieve some attributes, then you can actually visualize how the entropy or Gini index is being decreased along the process of branching. Okay? And that's a good point. So it's important to keep in mind that entropy or Gini index is the main criteria for splitting the regions or during the branching process, right? We don't want to go into too much details because this is not a really math foundational course of machine learning. But still, it's important to remember that we're actually looking at entropy or Gini index in every split. Right? We can possibly use different thresholds. For example, even for age, do I use 49 or 50 or 55? Well, it depends on how you can decrease the Gini index. Right? Each region resulting from your branching, you have a Gini index, and then we look at the overall average Gini index. Okay. All right. So should we grow a full tree? So that's the question important for us to think about. Perhaps not necessarily, right? Because we have some discussion about complex models versus simple models. The main idea is that if you do a fully grown tree for the training data set, you can achieve a training error of 0 because for each region it's pure, right? You have a region of blue points, so in the training data, you're always going to classify any point in the blue region as a blue class, and there's no discrepancy between the data points in the training set and your pure, fully grown tree. Right? But this is only for the training set. If you focus too much on the training set, remember the training set is not a perfect representation of the reality. The future data you want to make prediction about is going to be different, right? So you may have much worse performance on your testing data set, which is not seen by the whole tree construction or training process. So the key idea is that, well, not necessarily we want to do a full-grown tree because that may be leading to a model that is overly complex, leading to some issue we identified as overfitting, right? You fit the training set too well, this generally means that you may perform poorly on a testing data set. There are different ways we can control the complexity of a tree. For example, there's some parameter, some procedure called pruning. You may want to grow a complex tree and then you cut off some branches. But how do you do the pruning process? Well, there's a lot of details to be concerned if we want to really learn the method. But on the application level, the important thing is that there's some parameters for us to use to control the complexity level of the tree. There's some parameter value called cost complexity path for the pruning process, which we will use for controlling the complexity of the tree in Python codes. But we don't go to the details. The idea is that there's something we can use to control the complexity of the tree, right? And also there are some rule of thumbs which are also useful. Like we can control the maximum depth of the tree. Now, by the way, in terms of the depth of a tree, we can go back to this fully grown tree, right? And this fully grown tree will have a depth of, I think it's a depth of 4, right? Because you can consider the root node as level 0, the 0th generation, and then you go down the tree to see what is the number of edges you have to visit until you reach the farthest leaf node, right? So this is the first generation, and then you go down here 1 generation, right? You go down here 2 generations, and go down 3 generations until you reach the bottom leaf nodes. It takes 4 generations. So in this tree, the depth is actually 4, right? But we don't want to have such a complicated tree. Maybe I say, let's construct a tree of a depth of maybe 3, right? Then I should not do the splitting for the bottom 2 leaf nodes. Instead, I should treat this node instead a leaf node, right? So that's another thing we want to. Sorry. So yeah, and also maybe we can control the minimum number of data points to split a node, right? So let's say we obtain a region, and in that region, let's say I have 10 data points. Let's come up with a rule saying that for any region less than, with fewer than 15 data points, let's not further split that region, right? So we can stop there, which also helps controlling the complexity of the tree. And also the minimum number of data points in the leaf node, right? If you kept doing this, the branching, you may end up with only 1 or 2 points in a certain region, and that may not be desirable. That's one possible rule is that for however you construct the tree, however you do the splitting, let's not create a leaf node with fewer than 10 data points. Right? All those are rules we can use, and they are implemented as hyperparameters for the tree construction process. Right? And the purpose of doing those rules is that we want to come up with a relatively simple tree to avoid overfitting. Okay, so for example, this is a partially grown tree, not a fully grown tree, right? So we have stopped after branching the region on the right-hand side to the threshold of age equal to 49, and then the corresponding tree is fairly simple, right? And the prediction is going to be very simple, right? So for example, if we have a region, the average age is 55, the average income is 30,000, right? So we can easily get the prediction from this tree. So the average age is 55. It means that from the root node, I want to go to the right branch because the average age of the new data point is 55. It's greater than 49. I go to the right branch. Now the income level is 30,000, which is below the threshold here, 39,500 being the threshold. So if it's 30,000 as the average income level, I will go to the left branch, which is low, right? So that's how I can make a prediction based on the given features in the tree, okay? All right, so that's how we make the predictions, and there are some detailed information we can take a look at. Now, I would like to, again, inquire if there's any questions. If not, we're going to move on to the Jupyter notebook part to construct tree. All right, so let's go to this example. And the first step is, again, as usual, we're going to load the data set of car seat sales. So let's go back to Avenue to Learn. Data set for in-class examples. Let's look at the car seat, the second entry in this list. So let's copy the GitHub link. And then we can get started, okay? So let's do import again, pandas as PD, and PD, let's call the data frame just the car seats for simplicity, okay? So pd.dataframe, read CSV, and we can copy and paste the link, okay? And then we can, after that, we can do car seats.head to preview the data set, right? So again, essentially the same stuff we have done before, right? So this time the target value is sales, but right now the sales is in terms of numerical values. I mean, it's in thousands of units, right? So for example, the first row, 9.5, it means that we have 9,500 units of sale for the location corresponding to the first row, right? And then the features include comp price is the competitor's price. I mean, you have a competitor retail chain, right? They are charging $138, and then the income level is the average income of this neighborhood of your retail location, right? And this is the spending in terms of local advertising, right? How much money you actually spend on maybe printing out like flyers and doing some promotion on local radio stations and things like that, right? And population is the population of the neighborhood. Price is your price, as opposed to the comp price is the competitor's price, right? Shelf level location, this is a categorical variable. Actually, in this data set, we only have 3 possible values: good, bad, and medium. Right? You can imagine that if the product is placed on the eye level, it's the best location. Right? If it's in the bottom level, it's the worst location. I think if it's actually in a higher shelf level, it's not perfect. Maybe it's not medium. You can see it, but it's difficult for you to touch it, right? And the average age of the neighborhood and the number of years on average for residents of this area receiving educations, right? So that's the education level measured by how many years in school. And urban, that's again, urban area versus rural area, yes or no. And US, in this data set, US means whether or not that retail location is in the United States. It's actually a real data set from a car seat brand in the United States. So if it's yes, then the retail location you're looking at is in the US. Otherwise, it's in maybe Canada or other countries. Okay. So that's basically what's going on in this data set. I mean, here I reserved a cell for us to look at the aggregation level information of this data set, right? There are 400 rows corresponding to 400 retail locations, and there's no NA values, and then the columns are summarized here. So we do need to do some pre-processing. So this is just a detailed description of the feature variables I just went through. Now, here, I mean, you can directly try to predict sales level, right, as a numerical value, but here, let's actually make it a classification problem. Okay? So the way we are going to make it a classification problem is that we're going to determine the sales numbers. Is it above 7,000 or is it below 7,000? If it's above 7,000, I'm going to call it a high sales level. Otherwise, it's low sales level, right? So let's actually look at car seats sales. Let's look at the sales column. Okay? Before doing anything else, let's look at sales columns. That's a numerical column, right? But then I'm going to provide a condition greater than or equal to 7. And then same thing as what we have done before, right? True and false values to indicate if it's above or below 7,000. Okay. Now let's do one more conversion. So put this expression of condition inside a pair of parentheses, right? And then I will do else type int. So this basically converts all those true false values into integer values. I mean, as you can imagine, it's 0 or 1, right? So the first row has a 1 as the value of the condition. It means that the sale is high, above 7,000, right? Now what we can do is that I'm going to assign the result, this 0, 1 columns back to car seats. This I'm going to call it high sales, okay? High underscore sales. Now this basically creates a new column. That's our label, target variable label. Is it high sales or not, right? Now let's drop car seats dot drop the original numerical sales value, because to make it a classification problem, we don't need the original numerical value. We're dropping our columns or access equal to 1, and then let's do in place equal to true, so that the data set is actually changed after running this command. So let's further do car seats dot head. All right, so this is what we have after performing those 3 lines of code, right? Very easy. So first of all, we look at the original sales column to provide a condition to see if it's above or below 7,000, right? And then if it's above, it's high sales, so it's true. I'll convert it to 1. Right? If it's below, it's false. I convert it to 0. So this column of 1 and 0, ones and zeros, the last column is our target column to predict whether or not the sales level is high. Okay? And then I drop the original numerical sales column because for this example, we're not going to use it. All right, so then one thing before we move on is that let's take a look at the car seat high sales. Let's do a value count. Value counts. Okay. Well, we have 216 rows that has a high sales level. 184 levels have the target label being 0, meaning that it's a low sales level, right? It's not a perfectly balanced data set, but in general, it's okay, right? The difference between positive and negative labels are not that huge. So let's skip the undersampling or oversampling step, just to use it directly for the prediction model, okay? Now, the next step is, again, pre-processing. So because we have done this before, let's do it relatively quickly. So car seats dot head, just to recall what's happening there, right? 3 categorical columns: shelf location, shelf lock, and urban or US. Right, so those are the three categorical variables. So let's just encode those three categorical variables. In the handout, I actually tried to do a value count for those three categorical variables. So for now, let's actually skip this step. Instead, directly jump to the step where we want to perform one-hot encoding, right? So let's call the data frame after encoding, car seats encoded, and then we do pd.getDummies, right? And then we want to do car seats. Specify the columns to perform one-hot encoding for, and it's going to be shelf location, shelf lock, and then we have urban. It's a yes or no value, right? And finally, US. Is it in the US? Yes or no again. And then we can do drop first equal to true. D type equal to int. All right, so that we can visualize the encoded data set by using, again, the head function. Sorry, another typo. All right, so then it looks okay, right? So, for shelf level, we have two columns. It should be three levels, good, bad, medium, but then we dropped one, right? And urban and US, both are binary valued columns, yes or no, so we just have one column to indicate 0 or 1, okay? All right, so do we have any questions for this part? Just the pre-processing part, right? Then again, something like we have to separate the data into X and Y, right? So X and Y. So for Y, it's car seats underscore encoded, right? And then we use the column high sales. Remember, that's the 0, 1 column, indicating if it's a high sales level at a certain location, right? And for X, similar, we're going to drop the target variable. So drop high sales access equal to 1. All right, so then so let me see what went wrong. So car seats is not sorry about that. I didn't see any error actually. Drop. Oh yes, sorry about that. So for the Y variable, it's actually we need to use square brackets, right? So because we are just taking one column out of the whole data set, right? And round brackets is for the drop function. Functions are for round brackets. All right, so that's the same thing as before. And then let's do this relatively quickly. So again, from sklearn dot model selection, we want to import the train test split. All right, so then we can do xtrain, x test, y train, y test equal to train test split. And want to split x and y, right? So both feature and the target. And test size equal to 0.2, random state, any number, but here let's use 28. And we can do stratify equal to y. You know, same thing as before, right? I want to maintain the original ratio between 0 and 1s even after the split. Typo, sorry. All right, so this is the train test split. Now we come to the most important part, which is to build a decision tree model. Well, it's actually very easy in terms of implementation. Right? So what I want to demonstrate is that what kind of arguments you can provide to the model. And those are essentially hyperparameters. So let's do sklearn.tree. So in order to create a tree, you want to import the function that helps you construct a tree model, like what we have done for linear regression, logistic regression, KN, right? But then this module is called sklearn.tree. Very intuitive. For KN, it's actually sklearn.neighbors. This time it's tree. So we import decision tree classifier. It's a bit long, so let's import it as a DTC, right? Decision tree classifier, just to make it easy, right? And then this function is imported as DTC, so we can construct a decision tree. So we say tree equal to DTC as a function, okay? So we need to, if you just stop here, it's okay. So if you don't specify any parameter, any arguments, they just implement the default argument value. Yes, please.
Why did you set the test size in random stateful?
Which one? Oh, yeah.
You said, okay.
Test size is 0.2. Okay, thank you. Yeah. So DTC, we need to provide some arguments, but it's not a must, right? If you don't provide anything, that's also okay. They just set it to the default argument values. I actually included a table in the handout. You can look up for the default values for the different arguments. But now, just to better understand what's involved in this whole thing, right? So let's actually start to specify some values. So criterion is basically specifying which measure of impurity you want to use. And the candidates are Gini index and entropy, right? So let's do entropy. So another thing we can do is the max depth equal to, let's say 4, okay? You don't specify it, and it actually may give you a full-grown tree, but I want to make it slightly simpler. So there's also something called mean samples split equal to 5, right? It means that, well, if you have a region, after every branching, you are dividing a region into 2 subregions, right? You will need to make sure that each of the subregions will have at least 5 data points, right? So it means that if you already have a region with only 5 data points, you cannot further split it. And that also helps reduce the complexity of the tree by reducing the possible steps of branching, right? And there's also something called mean samples leaf. Let's say equal to 3. So in any leaf nodes, you need to have at least 3 data points, right? So it's similar to the previous argument. I think, just to clarify, the previous argument is that saying that if you have a node or a region already at or below 5 data points, you cannot further split it, right? And this argument says that for any resultant leaf node, you need to have at least 3 data points, okay? So then another thing is called max features. This is the part slightly tricky. So it's actually a string value. So here I'm going to put square root, sqrt. What does it mean? Remember we said for every step of splitting, we want to check different features, right? Do I split on age or income? In the data set, we have more than 2 features, like do I split on price, competitor's price? There are a lot of candidates, options, right? But sometimes I do not want to consider all the possible features to split. And that may be too complex and too time consuming, right? So sqrt means that, let's say I have a total of 16 features, as an example, right? Then I specify maximum number of features to split equal to sqrt. It means that square root of 16 is 4. So every time for splitting, I'm randomly selecting 4 features as candidates to split off, right? So I don't want to consider all the 16 features. Instead, every time I will do square root of 16 to consider only 4 features that we can, doing branching with respect to. Okay, so that's another feature. And there's another thing called CCP alpha, cost complexity, and that's typically in mathematics it's denoted by alpha. It's not important for us to learn the details, right? But the important thing is to realize that CCP alpha is a parameter that helps you control the complexity of the tree, right? In addition to those rule of thumbs provided as minimum number of samples to split a certain region or minimum of data points inside a leaf node, right? So 0.01 is a relatively small number. So it means that I want to control the complexity of the tree just a little bit on top of all the previously included criteria. Okay, so random state equal to, let's say, 28. Okay, so that's how we create a tree. And run the cell, you will get a tree already constructed. Okay, now after you have constructed the tree, the next thing is that we can already fix it, right? So, by the way, this is the list of hyperparameters or arguments, right? There's a lot of them. Well, it's I guess it's not that necessary to memorize the meaning of those parameters. Every time you need them, you just come back to this table or go back to the documentation of decision trees in sklearn to see if you want to specify some values for those parameters. Right? And another table for the default values of all of them. Let's save some time by skipping those and focus on the main idea. Okay. Now we can fit. So we have a tree constructed, and the name is simply tree in this example. And then I'm going to say tree.fit x train y train. That's actually completes the fitting procedure, right? So what it does is simply do the behind scene branching process for the tree. Okay, so things are done nicely for us. Then we can actually use it for prediction. Right? Same thing as before. So one nice thing about most of the packages in sklearn is that the syntax is essentially the same, right? So we can do tree.predict, and we can predict on the test data set, right? X test. Okay. If you want to do probabilistic prediction, that's also okay. Y prob equal to tree dot predict prob. So it's the same thing as logistic regression, right? So let's not spend too much time on that. And then you can construct things like the classification report and different kind of performance measures as before, right? So let's do from sklearn.metrics import. Let's import just one thing for here, classification report. Okay. And then CR is equal to, again, the same thing. Classification report is to compare the actual observations in the target variable of the test part of the data set, and then the prediction part. Okay, and then we can run it, and we can print the classification report. Okay, so as we can see, the accuracy is 65%, not too impressive, but also somewhat usable, right? Because it's better than your random guess. All right, so you can do AUC score. So in the interest of time, let me skip this part, and we can come back later to do some additional tasks. But there's one thing I want to show you before we finish today's class. Okay, so there's one thing which is to visualize the tree construction process. Okay, so the function I want to use is that I want to use a function to plot the tree. Right? I mean, in the slides we have seen the the diagrams representing the branches of the tree. Now what we can do here is that we can do from sklearn.tree, again part of the tree submodule, import plot tree. Right? So whenever we are doing some plotting, it's also a good idea to import matplotlib.pyplot as PLT, right? So because most of those things are somehow based on the matplotlib library, right? So then we can do the plotting tree, plot tree, and then we want to plot this tree, right? This is the tree we constructed and fitted, right? Now we need to specify the feature names, otherwise the tree is not going to be very readable after we plot it. Feature names equal to, well, we have x including all the columns, right? We're going to take x dot columns. Those are the feature names. And class names are the labels you want to use for your target, right? I mean, it's 0, 1, but it's a good idea to make it low for 0 and high for sales. Otherwise, it will show you 0, 1. It's okay, but it's not that nice in terms of readability, right? So let me show this. It's actually very small, so I think I need to do one thing. So let me do somewhere there. Let's do plt.figure. This allows me to specify the size of the figure. Fig size equal to the two-dimension values. Let's do 30 and 30. So I experimented before today's class to see what is the right size. Okay, so that looks nicer. So let's see if I can show you. Looks like it's not very. So let me do it again. Okay, so we have just a few more minutes. So maybe increase it to 50 and 50. Well, I'm not sure if it's much better, but anyways, the idea is that it constructs and visualizes the tree for you, right? The font size is fairly small, but then at least it provides the detailed information we need, right? So the first feature to split is the advertising amount. And the threshold is 7.5, right? And before the splitting, it has a line shows you the entropy, overall entropy, which is very close to 1, which is the bad news, right? Because it's not very pure. And then after the split, you have two branches. One of the branches is having 147 data points, and the remaining data point, branch is having 173 data points, right? And then the final line of this node in this box is class equal to high. Right? I mean that if you don't do any branching, just focus on the entire feature space, you will just count the number of high sales versus the number of low sales, right? And the majority one will be the label for the entire feature space before branching, right? Now, you keep doing this branching, things will become nicer and nicer if you focus on the entropy level, right? So because I mean, not every node actually have good entropy because you want to control the complexity of the tree, right? But then it starts with something very close to very close to 1, and then look at some of the leaf nodes, right? You have, for example, have an entropy equal to 0, mean that it's a pure node, right? And for other, branches in the middle, you have something like a 0.661. So it's again something in the middle, right? So, anyways, if you look at the leaf nodes, we will observe that even though some of the nodes still have relatively high entropy, but it's still a significant reduction based on the original entropy level. So this whole procedure of branching is to hopefully reduce the impurity measure as you go down a tree, right? And then if you have a tree like this, you can already make predictions based on, at each split, each node, you go to the left branch or the right branch. Okay, so that's how we can construct tree. We almost finished the decision tree, maybe with the exception of cross-validation applied to a tree. But I think that part is okay because next time we're gonna briefly talk about random forest, and then it's basically something we call the ensemble method that combines the prediction by a group of trees, right? And then we can apply cross-validation and other things we have learned to any classifier, such as the random forest classifier.